All right, this is section 7.4 on infinite geometric series, and this is really where I think sequence and series gets a little bit more interesting when you start talking about infinite series rather than finite. Finites are they're kind of boring. Consider the infinite geometric series 1/2 plus 1/4 plus 1/8 plus 1/16. This is one of my favorite sequences, by the way, because the story I tell is, imagine you have a cake and you serve half a cake. So there's the half, right? And then you cut what remains in half and you serve that. So there's plus 1/4. And then you cut that in half and you add 1/8, or you serve 1/8, right? And then you keep doing that. In theory, you could keep cutting what remains in half and serve half. But you'll never eat more than one cake. So this sum, as you keep adding it up, this infinite sum approaches 1 forever, never actually becomes 1. It becomes 0.999999999. But how many 0.9s do you need to actually say, well, now that's 1? What if it's 1,000 0.9s? Is that 1? I mean, how many do you need? It does approach 1. And so in theory, we could do that forever. So in theory, it does actually get to 1 when you get to infinity, or an infinite amount of, serving halves. We're going to find and graph the partial sum. So we're going to look at the partial sums for this and then describe what happens as S sub n as n increases, and I kind of gave it away. It's going to 1. So what about partial sums? So let's look at the first partial sum, and the first partial sum is just the first term, 1/2. And then the second partial sum, and let's use the calculator over here, on 1/2 plus 1/4. And so we went from 0.5 to, we can use decimals, 5.5. No, that's not right. No, because that's over 1, not 5.5. I missed a button here. 1/2 plus 1/4. There we go. 0.75. So the second partial sum is 0.75. So let's do a few more and see. We're actually going to the fifth partial sum, I guess. So then we're going to go plus 1/8. And it's getting higher, but not over 1 yet, and it never will be. 0.875, S sub 4, S sub 5. So S sub 4, let's see, we added 1/8, so let's add 1/16. And that's 0.937, Getting closer to 1, getting real close to 1 now. And then we're going to add 1/32. And that is 0.96875. So now really getting close to 1. Let's go one more, plus 1/64. So S sub 6, so we're going a little farther than what we're asked to, is 0.984375. Now, the whole point of this, the reason that you can add an infinite amount of terms and never get over a value is because we add less and less and less and less and less. You start to add something really close to 0. So if you add 1/64, 1/128, 1/256, that's already pretty small. Imagine cutting a cake into 256 pieces and serving 1 piece. That's pretty small. Well, imagine 1/1,billion or 1/1,000,000,000,000. That's extremely small. So as the denominator of a fraction gets bigger and bigger and bigger, the value of the fraction is heading towards 0. Now, in order to have a sum, in order to have an infinite sum, the terms must go to 0. You must eventually add something so small, it might as well be 0. Now, I don't even know if we're following the example. Find the partial sums. We can graph these. We can graph them. We know that 1 is 1/2. So up here at 1 would be 1/2. 2 would be 0.75. 3 would be 0.875. 4 would be 0.93, and what ends up is we're leveling off. We won't go above 1. We're leveling off to 1. Then describe what happens as S sub n as n increases. S sub n is approaching 1 as n approaches really infinity. Sum of infinite series. In example 1, you can understand why S sub n approaches 1 as n increases by considering the rule for S sub n. So let's say this is actually the finite sum that we talked about in section 7.3. Well, we just talked about how what you add has to get smaller and smaller and smaller and smaller. So consider this sum right here. Now, what we multiplied in this previous example is 1/2. That's why it's geometric. We keep multiplying by 1/2 to get the next term. So as long as r is less than 1, the terms will get smaller and smaller and smaller. So if r was 3/4, we would take 3/4 of the previous term, and we would take less, not all of the previous term. So that means the next term would get smaller and smaller and smaller. Now, if you multiply by something bigger than 1, like if you multiplied by 2, the values would actually get bigger. Imagine 1 plus 2 plus 4 plus 8 plus 16. Now that sum is headed off to infinity because you're adding more and more and more. You're not adding less and less and less. So let's get back down to this right here. As long as r is less than 1, let's say it's 1/2. If you take half to a big number, that's an extremely small number. So imagine 1 over 2 to the 1,000. That's a very, very small number. Imagine 2 to the billion. That's extremely small number. The denominator is very big, but the fraction is very, very small. So as you approach infinity, this thing right here is approaching 0. So we have 1/2 times, whoops, how did that happen? 1/2 times 1 minus 0, because as n gets really big, this fraction is getting really small. Then when it hits infinity, you're actually at 0. And then we have 1 minus 1/2, which is 1 minus r. So this becomes a sub 1 times 1 over 1 minus r. So the infinite sum, the formula for an infinite sum, this is where this is all headed. This is why we're talking about all this stuff right now, is a sub 1 over 1 minus r. It's an amazingly small formula to find the sum of an infinite geometric series. It's such a simple, beautiful little equation. A sub 1 over 1 minus r. The sum of an infinite geometric series. The sum of an infinite geometric series with first term a sub 1 and common ratio r is given by, and here it is, a sub 1 over 1 minus r, but provided that the absolute value of r has to be less than 1. So r could equal 1/2, r could equal -3/4, because if you take the absolute value of that, then that's going to be less than 1. So it has to be the absolute value. Find the sum of the infinite geometric series. Well, the first thing we're going to do is check r. Now remember, the nth term of a geometric series, of a geometric sequence, is a sub 1 r to the n minus 1. In this case, instead of n's, we have i's. So this right here, there's the r. So the r in this case is 0.8. Well, 0.8 is less than 1. R is equal to 0.8, which is less than 1. So we know we have an infinite sum. So the sum is a sub 1, which if we plug 1 in, 0.8 to the 0 is 1 times 5. So a sub 1 is 5 over 1 minus 0.8. Now that's 5 over 0.2. If we take 5 divided by 0.2, we get 25. So this infinite geometric sum, it will never get over 25. It will infinitely approach 25. Letter B, looks like we're multiplying by actually -3/4. -3/4. So r is equal to -3/4, and the absolute value of -3/4, which is 3/4, is less than 1. So the absolute value of our r is less than 1, which means we have an infinite geometric sum. The sum is equal to a sub 1. The first term is 1. Excuse me. So we have 1 over 1 minus 3/4. That's a sub 1 over 1 minus r. That's 1 over 1/4, because 4/4 minus 3/4 is 1/4. We can multiply the top and bottom by 4 because that's a complex fraction. And we end up with 4. So this sum never gets over 4. It always approaches 4. What is the sum of the infinite geometric series here? Looks like we're multiplying by -3. So r is -3. So the sum is a sub 1, which is 1 again. 1 over 1 minus, it's always minus -3. Oh, I did this one. Oh, shoot, I did this one wrong up here because it's negative. So we have the sum is 1 over 1 minus -3/4. That's equal to 1 over 4/4 plus 3/4 is 7/4. Now if we multiply top and bottom by 4, it's 4/7. There's the sum. Completely forgot that it's negative. So 1 minus, that's 1/4 there. So this one never gets over 1/4. The answer is letter A. Consider the series 2/5 plus 4/25 plus 8/25 and so on. Looks like we're multiplying by 2/5, positive 2/5. Find and graph the partial sums, then describe what happens to S sub n. So first partial sum is 2/5. 2/5. Second partial sum, let's clear this and let's go 2/5 plus 4/25. And I'm trying to, this is a little, this takes a while to do. So 0.56 S sub 3 plus 8 over 125. And so we're adding a little bit more. So 0.624 S sub 4. We added the 8. How about the 16 plus 16 divided by 625? So 0.6496. And then we're going to add 32 divided by 3125. And we have S sub 5 is 0.65984. Find and graph the partial sums. I'm not going to graph it. Then describe what happens to S sub n as n increases. S sub n is approaching, I don't really know. Let's figure it out here. Let's go. S is a sub 1 2/5 over 1 minus, and we're multiplying by 2/5. So that's 2/5 over. Now what we could do, here's an option. We could multiply everything by the common denominator, which is just 5. So when we do that, those cancel out. That's 2 over 5 times 1 is 5. Those cancel out, minus 2, and that's 2/3. So this is approaching 0.666666666, 2/3. So the sum approaches 2/3 as n approaches infinity, as we get to adding an infinite amount of terms. Here we have infinity on top, so this is not a finite sum, this is an infinite sum, where a sub 1 is 1. So a sub 1 is 1, and r is equal to -1/2. So the infinite sum is a sub 1 over 1 minus r, and r is -1/2. So we have 1 over, we can do this, how about this, 1 plus 1/2, minus minus is a plus, then multiply everything by the little denominator. That's 2 over 2 plus 1. 2 times 1 is 2. 2 times 1 is 2. These cancel, leaving 1. So this infinite sum is 2/3. Now let's look at number 3. If we plug 1 in right here, we get 0. 5/4 to the 0 is 1. So a sub 1 is 3, but look at r. R is equal to 5/4, which is greater than 1. So no sum. There's no infinite sum. The sum is infinity, but if the sum is infinity, we just say that there's no sum to that. Number 4, let's see, what are we multiplying by? We're multiplying by 1/4 to get the next term. So r is 1/4, which is less than 1. Actually, the absolute value of it is less than 1. But if it's positive, we don't really have to worry about the absolute value part. So the sum is a sub 1, which is 3 over 1 minus 1/4. Now what we could do is multiply everything by 4. That's the little denominator. And we get 12 over 4 times 1 is 4. Those cancel out, 1. So 12/3. The sum for this one is 4. Use an infinite series as a model. A pendulum that is released to swing freely travels 18 inches on the first swing. On each successive swing, the pendulum travels 80% of the distance of the previous swing. What is the total distance the pendulum swings? Now, we're assuming that this actually swings infinitely. It never stops, but the distance it travels gets smaller and smaller and smaller. So it fits that concept. It fits the concept that in order to have an infinite sum, you have to eventually add less and less and less and less. What you add has to tend to 0. So what is the sum? The sum would be 18 plus 18 times 0.8, 80% of the previous swing, plus 18 times, and then 80% of that, but you can always start back with a sub 1, plus 18 times 0.8 to the third, and so on. So this is n equals 1 to infinity. Let's see if this fits. Of 18 times 0.8 to the n minus 1. Here's your a sub 1. So the infinite sum is a sub 1 over 1 minus 0.8, which is 18 over 0.2. So 18 divided by 0.2. That's 90. So it's equal to 90 inches. Write a repeating decimal as a fraction. So 0.24. Now we can write this as 0.24 plus 0.0024 plus 0.000024 plus, and keep on going in that fashion, because if you add those up, 0.24 plus 0.0024, you see how the zeros match up with the digits that are not 0. 0.000024, and if we add that, we would get 0.242424, and we could keep going in this pattern. Well, this is 0.24 to start out with, and then it's 0.24 times 1 over 100, because, or divide by, dividing by 100, because it moves the decimal point over 2 places. And then 0.24 times 1 over 100 squared, because now you have 4 zeros. And then plus 24 times 1 over 100 to the fourth, to the third. Is it be the third? Yeah, because not fourth, to the third. So we could do this. N equals 1 to infinity of 0.24. That'd be a sub 1. And then 1 over 100 to the n minus 1. So the sum is equal to, now we're going to write this decimal, we're going to write it as a fraction, is 0.24 over 1 minus 1 over 100. Now we can multiply everything by 100, multiply by 100, multiply by 100, and that gets us 24 over 100 minus 1. Which is 24 over 99. Now, if we take 24 divided by 99, we get, look, 0.24242424, keep on going. Now, let's try a couple more of those. That takes a little bit of practice. So this is 0.5 plus 0.05 plus 0.005, and so on. So we're taking 0.5 plus 0.5 times 1 over 10, because we only have to move the decimal point over once, one time, and then 0.5 times 1/10 squared, because we're moving 2 places over. That would be 100. So dividing by 100 would move it 2 places, and so on. So this is n equals 1 to infinity of 0.5, and then 1/10 to the n minus 1. But the whole point is the sum, the infinite sum, now we're going to write it as a fraction, is 0.5 over 1 minus 1/10. Now we can multiply everything by 10 in this case. So we get 5 over 10 minus 1, 5/9. So if you take 5 divided by 9, you get 0.5 repeating. How about one more, and then we won't do number 8. So let's do number 7. This is 0.72 plus 0.0072 plus 0.000072, keep on going. So we can do n equals 1 to infinity of 0.72, and then 1 over 100 this time, because we have to move the decimal point over 2 places, to the n minus 1. So the infinite sum is 0.72 over 1 minus 1 over 100. So multiply everybody by 100, that little denominator. You know, this is a complex fraction. This is one way of getting rid of that complex fraction. So 72 over 100 minus 1, 72 over 99. I think you're kind of seeing a pattern here. I wonder what 13 divided by 99 is. I'll be darned. And then 72 divided by 99. There we go. 0.72 repeating.